Okay, well, welcome. So this is the last of kind of our mini segment, 4 sessions on software engineering, and it's been fun being a part of this and kind of bringing my perspective to the table and hearing your questions about software engineering. I definitely want to have some time today if there are things that are fuzzy or things you want to talk about, that I want to give you an opportunity to raise any questions or talk about any topics that, whether it's stuff we've already talked about or stuff we haven't talked about, questions you have from software. I'm happy to talk about that today. Here's our agenda. There we go. I didn't see much in the minute survey, so I'll just ask for questions there. I want to talk just a little bit about design patterns. We introduced one briefly, the facade pattern, on Monday, and we'll talk about a couple more. And then talk about software testing and test-driven development. And you'll see a number of things are very similar with software testing as they are with other kinds of testing, but there are some perhaps distinctions. And so we want to talk about why testing is hard and some of the challenges that we have and what we do about that. And then I'll wrap up with test-driven development. So that's just a particular area, maybe if you just had any software engineer talking about different topics, that would be one small topic amongst several others. But for me, that's a big area of emphasis where I've spent a lot of work and done a lot of research. And so I thought I'd spend a little extra time there talking about TDD, test-driven development. And that will wrap up our time. So before I jump in, anything you guys want to talk about before we try and I don't care if we don't get through this agenda, I guess is what I'm saying. If you guys have another agenda that you think is more important than software related, software engineering related, I'm happy to talk about it.
On that UML class diagram, I think I saw an email just a few minutes ago from you. I just looked at my email a few minutes ago.
Yeah.
So with the different user types, can you specify the permissions that they have of what they can and can't do? Or do you have to create a whole new block for that?
Okay, so let's make sure we understand the question there. When you talk about user types, what are we talking about?
I think it was a class type.
Okay.
The class name under the attributes.
Okay.
Is that where I know you're doing like the plus and minuses last time with like permissions, was it? Mm-hmm. And we set that in the users, or do we set that in the,
Okay, you mean like the visibility we're talking about, public, private, and protected? Yeah, yeah. And so what we're talking about there is not regarding actual people or users, it's actually regarding the software itself. And so let's make sure that we understand that. Let me pull up a class diagram real quick. Let's see what would be a good one. In fact, I think, can I pull this one? Brad's up. I think that would be fine. Let's pull this one up. So this is one that was created and turned in this last week. And so I think this can be a great example. Let's look at. And so in this example, there's 4 classes that were identified. And one class is the vehicle tier, another class is the vehicle model, and then a reservation and a rental office. And those are all great classes, class names. So they're entities, they're things. It's a grouping of software is what it is, that all goes together, all belongs together in some logical way. And again, a class like this one, the vehicle model, it has the class name in the first section. In the middle section, it has the fields. And so there's 2 fields there. It has a vehicle model or a model name and a is available. And then the third section here is the operations or the functions or methods. And so reserve model is the operation. So the idea is that this class has these 2 attributes, which are data values, and each data value has a type. And that's great that Brad put types in here. And so a model name is a string, is available is a Boolean. A Boolean is a true or a false value. Okay, and then there's other basic data types like integers and doubles. Doubles are real numbers, so like 7.36, for instance. And there's different sizes of real numbers. And so you might see float or double or long double. Those are all just real numbers, like 7.36. It's just a matter of how much space in the computer are we reserving. So how precise or how large of a number can we store is the difference in those data types. And I can talk lots more about that if you're interested. I don't know. Do you want to hear more about difference between floats and doubles and all that? No. Okay. So they're just all real numbers. Integers are whole numbers, counting numbers, 1, 2, 3, 4, 5. We know those. And then strings and Booleans, and then usually there's char, a single character. And so a string is a collection of characters all together as a single unit. But char would be just one character, like the letter D, a single letter. So those are basic data types. And what we're doing here is a class is basically a compound data type. So the basic data types generally hold one element, or like a string, a collection of elements that are all the same type, which a string is just a collection of characters. Okay? But all of the others are just basic data types. They hold one value, either true or false, or a number. But then a compound data type can have multiple values in them, and they can be of different types. And so that's what we see here. So now I have this new data type vehicle model, which has two data elements in it. So it's a compound data type that has two different elements in it that are of different types. So that's different from a simple data type where it just holds one value that is of a single data type. Does that make some sense?
Yeah.
Okay. And so that's really all a class is to start with, is it's a compound data type. But then we also associate with the class the methods or the operations that are the methods that operate on or that manipulate or use the data elements in that data type. Okay? So reserve model is probably going to change is available to false. Okay, assuming is available was true to start with, it's probably going to just change that variable is available to false, is what I'm guessing reserve model, the method, will do when you call that. Now, who calls that method? Probably it's some method in this class, or a method in this class, or a method in this class. It's some method in a different class is going to call the reserve model method in the vehicle model class. Okay? That plus there indicates who's allowed to call that method. And the plus, because it's public, it means any other class can call that method. If it was private, if it was a minus, then that would say that the only methods that can call that method would be in the same class. And so there better be some other methods in that class that are able to call that method. Okay? And so in terms of visibility, we're not talking about who can call the method. We're talking about which methods can call the method. You know, where are those methods that can call this method? So it's just a matter of, it comes down to this word I'd used at the beginning of encapsulation. We want to encapsulate everything about a vehicle model into this one chunk called, which is a class, the vehicle model class, so that it's all located in one location, and we limit mistakes because bugs are too easy to introduce into our software and they're too hard to find. And so that was one of the great innovations of object-oriented programming, was to encapsulate everything into a single chunk so that it's all isolated to one location. Everything that deals with these operations and methods are in the same place. Does that make some sense?
Yeah.
Okay. And so since this vehicle model is now a data type, I can create different instances or variables of that data type. So just like is available is a variable of type Boolean, it's one instance of the Boolean type. I could have another Boolean. Let's say I don't have, yeah, I do. Over here, there's another is available of type Boolean. So this one, it happens to have the same name, but it's different from this is available because it's in a different class. But it could have had a different name. Here's a better example. We've got tier name, which is a string, and model name, which is a string. So I have two instances of the string data type. Here's one called model name. Here's another one called tier name. They're both strings, but they're independent of each other. They just have the same type, meaning that they hold the same kind of data. They don't hold the same data, but the same kind of data. Okay? So I might say that model name is going to be Camry, whereas over here, tier name is going to be economy or luxury, something like that. Okay? And so each one, when we're actually running the program, each one gets its own chunk of memory. Okay? And so in a chunk of memory, you can store the name Camry in that chunk of memory, and you can store the name economy in this chunk of memory. Even though they're both strings, they're in different locations in memory. Okay? So in the same way, a vehicle model is a data type. And so I can create an instance of the vehicle model. So I can allocate a chunk of memory for one vehicle model. So let's say I create a vehicle model called, my car. Okay, so my car is just a pointer, a reference to that chunk of memory. And in that chunk of memory, it has a model name chunk of memory and an is available chunk of memory as well, where I store the data for my car. Then I could have another variable called your car, which is a type vehicle model. And so it has its own chunk of memory. They both are the same data type. They're both of type vehicle model, but they're two different instances of that type. So they both have a string called model name and a Boolean called is available, but those two variables can have different values in them because they're in different memory locations. Does that make some sense? So a vehicle model is just, it's a class, it's a template for an instance. It's what we call a compound data type. Okay. And then we can have these methods on them as well. Okay, so a class diagram is one view of the design of our system. And it's a static view, is what we would say. Static meaning that it's not showing how the system changes over time. It's just showing how it's organized. Okay? And so what's an example of, the opposite of static would be dynamic. What's an example of a dynamic diagram, UML diagram, that shows a different, the dynamic nature of a system?
The activity diagram?
Yeah, exactly. An activity diagram shows the process, the flow, the order in which things happen. And so that shows the dynamic nature of the system. Okay? Whereas class diagrams show the static nature of the system. What are other static diagrams? Can you think of any others that we looked at? It's maybe a harder question. What other diagrams? So let me give you, multiple choice question. Which of the following, choose all that apply. Which of the following UML diagrams are static diagrams? And so I might say activity, sequence, class, package, and deployment diagram. Okay, maybe you don't even remember package diagram. We just talked about it real briefly. Deployment as well. But which of those are static? Which of those are dynamic? So again, activity, sequence, class, package, and deployment.
Well, package is a collection of classes, right? So that would be static too.
Exactly. It shows how you're organizing these classes into packages. Yep, it's static. Good. What else?
I mean, it doesn't typically show how data flows through it. So I guess the deployment, because it shows, the individual, like just the architecture, what's going to be where.
That's right. That's right. So that's also a static diagram. A deployment diagram shows what are the components of software and where will they be residing, where will they run. It doesn't show the order and that they're running or the flow of control through them. Yeah, so that's also static. And then the others are all dynamic. So a sequence diagram shows the flow of the order of method calls and the collaboration between the classes. And let's see, did I list another one? Activity diagram was the other one that I listed. And so that also shows the order in which things happen. And so that would be a dynamic diagram. Yeah. So it's kind of like, you know, when you're building a building, we've talked about this before, software design is very different from physical design, but there are similarities. And so when we talk about designing a building or designing a bridge, but you know, certainly designing a building, what are the different kinds of diagrams we might have in designing a building? You know, what would you give to an architect, or what would an architect give to a builder in order to actually go and build it?
Blueprints. Blueprints,
yeah. And so a blueprint is going to show kind of a top-down view, right, of what the, you know, two-dimensional layout of a floor is going to look like. Okay, does that tell you what the front is going to look like, what the entrance is going to look like? No. And so the architect might give you what in order to tell what does the front look like? Do you know what they call that? A front elevation, I think is what they call that. So a front elevation, it might just be, you know, a picture basically that they've drawn that shows, you know, the doors and the windows and you know, the eaves and, you know, what it might look like from the street view would be a front elevation. And that's really useful to have those two, both the blueprints and the front elevation, to give you an idea of what the building is going to be like, of what the design is, right? You know, if you only had the blueprints, you wouldn't get a full picture of what the building's going to look like. And then similarly, you know, neither of those are going to have the full electrical diagram or the plumbing diagrams. You know, those are other diagrams that might get added onto the blueprints as well. And all of those are useful in getting the full picture of what the building's going to be like. It's the same way with UML and software. We need multiple diagrams to get the full picture of how the software is going to work. The class diagram is the most common of all the UML diagrams that software developers use, but it only gives you one view of it. It just tells you the structure of what are the different elements in how am I going to organize my code. But it doesn't show you, you know, how it's going, the code's actually going to work. And that's where we need like a sequence diagram or an activity diagram. Yeah. Is that helpful?
Yeah, thank you.
Okay. Any other questions related or unrelated you've got? Related? Okay. Let's look at, well, let me just mention, since we've got this up, there were a couple of other activity diagrams that were shown, and they were both great. Let's see, do we see any problems with this one? We've got an activity diagram. We've got this initial state, a start state, and down at the bottom, yep, it's got a final and ending state there. It's got all of these activities in between, and it's got some selection boxes there, conditionals where it's an if-then. If the login is valid, then we continue. If not, we go back to account login. If the tier is available or the model is available. That all looks pretty good. I had one other here. Let's look at that. So again, we've got a start and a stop, a beginning and an end state. This one has, what do we call these? Vertical or the horizontal bars there? Call this a fork and a join. Okay, and so we can fork, and so these things, select date and select vehicle, can happen simultaneously, and then they merge, they come together here. We again can have a question. I would say the only thing I would change here is this line here coming out of the other line probably should come directly from the diamond there. So check inventory. If the vehicle's in stock, so it should come out this way and over here to vehicle in stock. And then if not, we go up here to vehicle not in stock and come over here. And vehicle not in stock and vehicle in stock, those, I don't know that those are actually activities. those are maybe just labels. So I'd probably put that as a label on here, just text that said, check inventory, vehicle not in stock, then we come back up here, vehicle in stock, then we go over here to make reservation. So I'd probably not make these activities. But other than that, it looks great. Cool. Okay, well, while we're on, let me come back to my slides. Let's jump into our next couple of things. I want to talk about design patterns, and there we'll use a little bit of UML again. So I just want to talk about 2 design patterns. There's a bunch of them out there, and I'll just mention that. So GOF, this stands for the Gang of 4. There's these 4 authors on a book called Design Patterns, Elements of Reusable Object-Oriented Software. This book came out in the mid-90s, I think it was, and it became the most popular software book, probably still the most popular book ever sold. Everybody went and bought it, and there were, inside there were these 23 patterns. And there's many more design patterns than that now, but those are kind of the common core 23 design patterns that every software developer would know. So I mentioned facade, that was one of them. Here's adapter. You guys know what an adapter is. We've used physical adapters many times. Things like electrical plugins, for instance. When you travel overseas, our little 2-prong or 3-prong plugs from our computers or whatever, they don't plug in Ireland or in France or whatever, and different countries have different style of plugs. And so what do you need? You need an adapter in order to go from our 3-prong to their 2-prong or whatever it might be in another country. Okay, so it allows one interface to work with a different interface is basically what an adapter does. And we have the same concept in software. We want to be able to convert the interface of a class into another interface that the clients, meaning the client code, expects. The adapter lets classes work together that otherwise couldn't work together. Okay? And there's 2 kinds of them. So let's look at an example here real quick. So this is what our UML looks like, just at a high level in a generic way. So we have some code, and it wants to call a method. It expects a certain interface here, or a method or set of methods on some target, but we would like to have it work with a different class with a different set of methods. And so what we do is we put an adapter in between them that says, oh, I know how to convert. You call request, and I'll convert that to call specific request, is basically what it will do. And so it allows your client to not change. And the reason is, often you'll have client code. There might be 100 examples or instances of client code that are using this target class and calling the method request. And you want to change that target class to be this new adaptee, this new class that has a different interface. You don't want to have to go and change your 100 different client classes. That's a lot of work. It's very error prone. You might introduce new defects when you go and have to change all these clients. So instead, you just introduce this adapter, is the idea. And so it's a simple idea. There's actually 2 ways to implement it. This is the class adapter approach, in which we inherit from the, we implement the targets interface and we inherit from the adaptee. The second approach is an object adapter approach, in which rather than inheriting from the adaptee, we contain an instance of the adaptee. This line here just means that we have a reference to the adaptee. Okay. And I mean, I could go into a lot of detail as to what are the implications of that, the idea of a 2-way adapter, but I'm guessing you don't care very much. The main idea is just that we can introduce this new adapter class that allows us to keep all of our clients the same. They still call the same request method, but it changes it so that it uses a new class. Why am I, when does this happen? This happens a lot, actually. We have software changes all the time. So like I do a lot of Android development, and Android SDK that comes from Google, it's constantly changing. Every year, at least, we get a new version of Android. And so they'll introduce new classes that you're supposed to use. And these classes will do things in different ways. Like, for instance, you might have a class that allows you to have a list of things visually in an app. So like imagine the Gmail app. It has a list of emails, okay? And so they have a list class that you just connect to your actual emails, the data, and it knows how to display them in a nice list. And it gives you all sorts of things, like you can swipe them away to delete them, and you can long press on them to edit them. And so it gives you some of that functionality there. Well, they came out with better list classes, you know, a more efficient, a faster list class, especially a class that might, if your list contains a combination of text and images in it, so like there's a little picture there, and it's having to get that image from a server somewhere. So like, let's say you had a YouTube app that had a list of videos, and you wanted to have just a little image of each video there. Well, they came out with a list class that is able to retrieve those images faster than the previous one. Okay, well, I'd like my app to use the new list class, but I've got a bunch of places in my app where I use the old list class. And so that's the idea is I'm used to calling this method in my list class, but I want to call a new class, use a new class. It's a lot more efficient, it's faster, it knows how to work, but it's got a slightly different interface. So I place an adapter in between, and my client code can still call the old, think it's calling the old one, but in reality it'll redirect it to the new one. And I'll get to take advantage of the new way of doing things. That's the concept here of the adapter. Yeah.
This is where I'm a little confused with the arrows and everything. So I see that the client goes to the target, and then the target goes down to the request, and then that request is like looks at the adapter.
Right.
The adapter has already seen this the new request.
Right. So let's talk about what these different arrows mean. Okay. So this first arrow, this dotted arrow with just the simple arrowhead here, that's a dependency or a unidirectional association, but a dependency. It means that the client knows about or is dependent on the target. Basically what it means is some method in the client class is calling a method in the target class. Okay, so it's calling the request class. Okay, so that's what that arrow means. This arrow here is different. This is like the generalization arrow that we talked about on Monday, but because it's a dotted line instead of a solid line, that means that this thing up here is actually an interface and not a class. Okay, for now you can ignore that. We'll come back to that. But what it means is that the adapter class here is implementing this target, meaning that it's got the same interface. It has the same method names in it. Okay, so the target has a request method in it, so the adapter has to have a request method in it also. That's what that implements arrow means. Okay, so it doesn't mean the adapter is calling the target. It's very different from this arrow. It means that the adapter is a special kind of a target, or it can be substituted for the target. It can replace the target because it has the exact same methods in it that the target has. Does that make some sense? It's kind of funky.
Yeah, just like the adapter is basically just an addendum onto the request. Yeah,
it's saying that the adapter can do everything that the target can do, but maybe a little bit more, or in a different way.
Okay.
Yeah. That's what that arrow indicates there, that the adapter is implementing the same interface, meaning it provides all the same services that the target does. Basically it means it has the same operations, but maybe it redefines those operations to do something different, or it adds additional operations. But at a minimum, it provides the same operations that are in the target. That's what this line is guaranteeing. So that means that it can be substituted for the target. Wherever there's a client that uses the target, you can now substitute it, and the client can use this adapter, and everything should work. That's what it guarantees you. So substitutability. You can put this thing in place of that thing.
Okay.
And then we've got a third line here, and that means something different yet as well. Okay. This line is more like the original line here, meaning that there's an association between the adapter and the adaptee. But here, it's a solid line, and it's got this diamond that's filled in. And so this is the concept of composition. And I skipped that the other day because we were kind of running out of time. The difference between composition and aggregation. And the idea here is that the adapter contains one of these adaptees. Okay, up here, the client doesn't necessarily contain the target. It just knows about or uses the target. But here, it's a stronger form where not only does the adapter call the methods in an adaptee, but it actually contains the instance of this. And what the implications there are, if the adapter goes away, like it goes out of scope or you delete it, then the adaptee also gets deleted. It goes away. They have a common lifetime. Okay. Whereas up here, this arrow does not indicate that same common lifetime. Here, the client could go away, but the target would still exist because maybe there's other clients that are using that same target. Okay, so this is a weaker form of that association between the client and the target. This is a strong association between the adapter and the adaptee, meaning if this thing goes away, then that thing also goes away and it doesn't exist anymore. Okay. Generally, I'm going to say you guys probably don't need to worry about those differences. You know, those are details, and the reality is you can go into a tremendous amount of detail on UML, and most people don't need to know that much detail. You just need to know the general concepts of, oh, these things are classes. Those arrows mean that this is using that class. This kind of an arrow means that this is a special kind of that class. And here it's, again, a line saying this has one of those things in it. An adapter has an adaptee in it. Okay. You're asking great questions, Garrett. What other questions do you have?
That's it for right now. Okay. On this one.
Okay. Okay. So there we go. That was the design pattern, the adapter pattern. Kind of relatively straightforward. The next one is going to look a little more complicated just because I have a bigger example. This one I just talked about in general terms. The next one we're going to look at is called template. And if you think hard about those names, a template and a method, you can probably guess what it does. So what's a method? A method is like a function. It's got a series of steps that it will do, things that it will do, and it might return a value as well. Okay? So you call a method, and it does some things, and then it returns. Okay? That's what a method does. So a template method would be a sample of a method that you might make changes to. Okay? But the template or the format, the steps in it are the same. So the intent here is to find the skeleton of an algorithm. An algorithm is just a set of steps in an operation or a method, deferring some steps to subclasses. Okay, so meaning that we're going to have some steps in this algorithm, but we're not going to define them all right here. Some of those steps we're going to just say it's a placeholder. And in a subclass where we inherit and have the same method, then we'll fill in the details. And in fact, we can have 2 or 3 or more different subclasses that fill in the details in different ways. So let me give you an example. This takes a little minute to set up. So this goes back to my days when I was at Sprint. I talked about that at the beginning. We were doing telecommunications fraud detection, and we had these rules that we would run when calls would come in. We would look at the calls and try and decide if it looked like it was a fraudulent sequence of calls or not. And one of the rules that we had was a velocity rule, meaning like if there are a bunch of calls in a short period of time, that makes us nervous. Okay, that the rule should fire and say, you know, if there were 30 calls in 10 minutes on a single calling card, probably there's something suspicious going on, right? So that's what we would call a velocity rule. And that was different from the rules where it was just a single call, like one call from a payphone in New York City to United Arab Emirates was probably fraudulent. There we're just looking at one call. Here we're looking at a velocity, so a bunch of calls happening in a close period of time. And we had two different kinds of rules, velocity rules and international velocity rules, and we treated them a little bit differently, but they were very similar. So we had this run method in the velocity rule, which was a template method, and it had some steps in it that would vary. So let's look at those. You know, I'm going to skip that. Don't worry about that. Let's look at the UML. So here's our class, the velocity rule. And it fits into the context here of the other stuff, like there's a class of rules, and then there were different kinds of rules, and this is one sample kind of rule. And so you can see that generalization arrow, meaning that we've got inheritance going on. So velocity rule is a special kind of a rule. And international velocity rule is a special kind of a velocity rule. And so what that means is there's a run method up here, so there better be a run method here. Sure enough, there is. And there better be a run method down here as well. And it's not showing, but it's implied because of that arrow that there must be one in there. Okay? And then over here we have a rule base, which has a collection of these rules. And there, that's just like that composition we had before, but it's a little bit different. It has a white diamond instead of a solid diamond, which just means that it's a collection of rules, but the lifetimes aren't tied together. Okay? And then the rule base also has accounts and calls. We don't need to worry about much of this for this example. So the main thing we're looking at here is we've got this run method in the velocity rule. So let's look at that method. So here's the velocity rule class. It inherits from the rule class. Okay, so that's what, this is an example from C++, is the language. Okay, this is the way that you indicate inheritance, this colon public rule. So that first line is the same thing as this arrow here, saying velocity rule inherits from rule. Okay, so there we have class velocity rule inherits from rule. And inside here is a public method called run. It has one parameter, which is an account, and it returns a rule priority. And then these are the steps that it does. And it's got a while loop in there, it loops over, and then at the end it returns the result of calling another function or method. So we've got all these different method calls inside of here. Wherever you've got those two parentheses, it's calling another method in another class. And so like here, account is another class, and I'm calling a method on the account A, calling get last call on A, get start time on C. Okay, and you can come back over here and you can see that account is this class and call is this class. And you can see, for instance, I've got get the beginning, get last call. These are methods on the account class. And so get last call, I'm calling a method on the A, which is an account class. Okay, so you're learning some programming here. Okay, making you look at some code. Maybe that's new and scary and cryptic, but it's part of what we're just trying to do, get a little exposure to the code. Okay. Any questions so far? I'll walk through how it's a template method yet, but just trying to wrap your head around a method and what code looks like. Okay. All right. So the point here is that there are some method, some steps in here in the run method. This is what you do. You call a.reset, you call a.getLastCall, you call c.getStartTime, you call init. Oh, now this one's different. Init doesn't have anything in front of it. We're not calling the start time on a C, which is a call, or the reset method on an A, which is an account. We're calling init with nothing in front of it, which means that init is a method in this class velocity rule or in the parent class rule. In fact, let's go look at that. Init is in the velocity rule class, so it's another method here. Okay, so run is calling init. Later on, it calls fired as well. Down here, we can see where it calls the method fired. Okay. So the point is, at each of these places where it calls init and validate and fired, those are methods in this class. And those methods look different in the velocity rule and in the international velocity rule class. So here, for instance, is the fired method. Fired says if the count is greater than or equal to velocity, then we return a priority. Otherwise, we say that the rule didn't fire. But in the international velocity rule, it says if the count is greater than or equal to the velocity and the international count is greater than the international velocity, then we return the priority. Otherwise, we're going to return not fired. Okay. So the point is that we've got two different versions of this same method fired. One of them in the velocity rule class, one of them in the international velocity rule class. And we define them in our template method up here. This is our template method. So we have the same structure, but it varies whether we're doing a velocity rule or an international velocity rule. Okay. Pause for a second. So that's the concept of template method. Maybe we got lost in the details. That's okay, but the point is we've got these design patterns out there, and this is a way of passing on a good idea, a good design solution to other software developers. And that's one of the aspects that we think about when we're doing design and when we're doing actual implementation, coding in software engineering. So that's the third of the design patterns. Any questions on those?
So this last one I'm trying to kind of conceptualize. Is it kind of like the idea, like let's say I had a method for like jump, and I wanted, like I had another class, you know, and I was worried about, and I was trying to like dunk a basketball, and another one I was trying to clear a high jump, but in both of those I would call the template method jump, but I would have like different values for things like speed and height, and that kind of a thing, and then I would be able to call that template method, passing it different values for like the speed and the height depending on what context you want to use it in.
Yeah, somewhat. Okay, so the different values, if you're passing them into the method, then that's just what we would call parameters that you're passing to the method.
Okay.
If in the jump method, you've got a series of things that you do, like you start moving, you take a step, do you jump off your left foot, or you jump off your right foot, or you jump off both feet, or whatever. And so you have a set of steps there, and in one, at step 2, maybe you do a different thing if you're trying to dunk, and a different thing if you're trying to, whatever, do a layup, for instance. Does that make sense?
Yeah, it does.
Yeah.
Thank you.
Yeah. So you have an algorithm, a set of steps, and you just figure out, okay, what part of this algorithm varies? Oh, this varies. Here we do it this way, here we do it that way. So you put it in the template method, and then you let it vary in the 2 subclasses.
Got it.
Yeah. Good job. All right. So that's going to kind of wrap up the stuff on design that I was talking about. We kind of dove deep on some things, stayed real high level on other stuff. I just wanted to give you a flavor of some of the things in software engineering there. I'll skip over this. And I wanted to move on to stuff on testing and quality and test-driven development. Now, let me check. I'll bet we're about at, we're just about at 5 o'clock, so maybe it's time. Let's go ahead and take like a 5-minute break now, since we're naturally in between sections, and we'll come back. Let's see, what do I have on this? According to this, it's 4:57, so like at 5:02, 5:03, we'll start up again. That sound good?
Sounds good.
Okay. Hey, you're just in time. We just took a break.
Yeah, I just noticed that.
Yeah, that's all good. We just finished up talking about kind of the software design stuff on through some more design patterns. We're going to start talking about some quality and testing topics to round out the software engineering things.
Okay. Yeah, it's pretty bad timing on my part. I just seem to have this meeting that goes a long time at the very end of the day. It's bad scheduling.
Meetings. I know.
Yeah.
I know. Too many meetings. Sometimes it feels like my work consists of emails and meetings.
Yep. And then sometimes doing your job.
And sometimes doing the job fit in between all of that.
Right.
Yeah. But I have to remember the meetings are the work. It's where we get the work done sometimes. And the emails are, there we go.
Coordination is half the battle.
Yeah. Yeah. All right. Well, let's get started again. So I'm going to, actually, I'm going to pull up one little thing that I thought I would show. This is kind of an odds and ends picking up from way back at the beginning. I thought maybe I should have shown at the beginning, here's a sample tool that I use for doing early mock-ups, user interface mock-ups. And so this is kind of unrelated. This is just a little parentheses between topics, but something from back on the first day that we were talking about. This is a tool called Balsamiq. There's many other tools like it. There's things like NinjaMock is another tool. And what this allows you to do is to create these different screenshots and a little bit of a mock-up, and you can walk through something very quickly and get the idea of what should the user interface look like. I can click on one of these screenshots, and you can even set it up so that you can do an interactive demo, and you can click on these things and from one screen have it take you to the next screen, and so that you can just do a nice user flow demo and see how you would flow through the app before you build anything in software. And so if I go click on edit here, you'll see there's just a whole palette of things that you can drag and drop onto onto there. So if I want to put a color picker on there, if I want to drag a combo box, I can drag it on there and move it around. And there's a wide range of different kinds of things, different kinds of charts and containers and forms and layout elements and all of this. And so it's just a fast way to build a mock-up before you actually go and build something. And sometimes it's really great when, as a software developer, your user comes to you and has already thought through this and says, well, here's a mock-up. This is what I think the user interface ought to look like. And that can jumpstart your development. Just thought I'd point that out. There's these great online tools for doing things like that. Okay, so let's go talk about some software design and some software testing topics. We kind of finished our requirements, design, and development things. And so I thought I'd start with this slide. Maybe you've heard this before from Philip Crosby, the concept that quality is free, but it is not a gift. Okay? What do they mean by that? What does that mean? How could quality be free? Isn't it expensive? Don't we have to spend a lot trying to build a high-quality product? Why would they say that quality is free? You see a couple of hints down here that kind of get you to it, but they don't completely answer the question. The answer to the question is basically quality is free. I've also heard it said this way: quality is free, but only for those who are willing to pay dearly for it. Okay, seems like a contradiction. You mean I have to pay for it, but it's free? So the idea being that if you invest in quality, then it will pay for itself. That investment will return savings in the end. Okay, so if I spend an hour trying to make sure that whatever is of high quality, hopefully I'll save myself 2 hours later on having to try and figure out what was wrong with my product. That that I just won't even have to spend those 2 hours because I avoided the problem in the first place. That's the concept, that by investing in quality, you'll save money in the long run. So we talk about that a fair amount in software engineering. How do we build quality into our software? Defects are a major problem. Software is buggy. It just we have a horrible track record. It's amazing that we're still doing software with our terrible track record of how buggy and how defect prone software is. Why are we still doing software? Seems like we would have just thrown it out and said, that's a bad technology. Let's not do software anymore. We've had all these software failures. People have died because of bad software. But we haven't come up with a better way, okay? We can't do it faster or higher quality in hardware necessarily. It's usually slower to build things and put them into hardware than it is to build them in software that runs on general purpose hardware. And it's just as hard to make things quality and defect free in hardware probably as it is in software. Okay, so what are some of the things that we do about that? We can do a lot to build quality into our application as we go, but then we always will have to do some verification and validation at the end. We want to find out, is the system correct? So what's the difference here? Validation, is the system correct with respect to some specification? And verification, did we build the right system? Now, I'm always getting those words backwards. Okay, which one means which? And I don't care which is which. They always tend to go together. You need to do both of them. Okay, but the idea of validation, that looking at our requirements, did we build it right? So does it meet the requirements? Is it done? Is it complete? Is it correct? Are there defects in it? But then verification, did we build the right system? So who cares what the requirements were? Is it useful? Does it meet the needs of the user? And so that's what we're looking at. And so under these V&V activities are all sorts of things that we do to attempt to ensure that the software will function as required. And so what are some of these things? We do a lot of code reviews and software inspections and walkthroughs where we just have people who know software that look at each other's code. And that's actually one of the most effective ways of finding and removing defects and making sure it's of high quality. The problem is it's time consuming. It takes a long time, and generally in most code bases, you don't get more than 10% of the code formally reviewed by peers. It's just too time consuming. Right? So what else do we do? Other things are testing to check to see, does it do what it's supposed to do? And there's different kinds of formal and informal methods, and we'll talk about a few methods here in a second. We can do dynamic testing, in which we're actually running the code, executing the code, or static testing, which we do, like we talked about, reviews, software reviews, or formal verification, where we have a code that reasons about the code. It doesn't actually execute the code. It just looks at the software itself and can mathematically, verify that things are true or that it's sound. We have different levels of testing, and maybe I'm gonna jump ahead on that. What are some of these levels of testing? And in fact, let me even jump ahead here, and then I'll back up again. So where can I put this? There we go. We'll put it up on top. So this is our big V, and maybe you've studied this, and it's very similar in software engineering as it is in systems engineering. At the beginning, at the highest level, you've got your user requirements, and then functional requirements, and then the software design or architecture, and then the actual code that you built. Well, what are the corresponding mechanisms, quality mechanisms for verifying that that is of good quality? Well, with code, we do unit testing, and usually that's at a method level. We showed some examples of functions just earlier today, and so we might write a test that tests a method in code, and I'll show some examples of that when we talk about test-driven development in a minute. And then at the architecture, we'll do integration testing. We'll put multiple components of the software together and see, do they work together correctly? Okay. And then the functional requirement systems testing, where we'll put entire subsystems together with other subsystems, or we'll test an entire subsystem from a functional way. Give it some inputs, does it give the right outputs? Okay. And then from a user requirement level, we do acceptance testing, and so that's generally just manual, where The customer, the user will walk through and say some sample tests and say, does it do this correctly? Does it do that correctly? These are these different levels. I'll back up a little bit and talk about these things just a little bit more. So with unit testing, we often are talking about what's called white box or clear box testing because we can see inside the code. We're looking at the details of the software and testing it based on what we see there. Whereas when we're doing functional testing, we're usually doing black box testing where we don't know what's inside the code. We just know how to call the code, how to give it values, see what it returns. Other kinds of testing that wasn't in that list, regression testing. That's where we retest previously tested components because we've made some change. We want to make sure we didn't break something we didn't intend to break. And then things like stress testing and load and performance testing. So how many transactions or how many users or how many events can the system handle? Maybe it works fine when there's 100 users, but then all of a sudden when we get above 1,000 users, it starts to break down and can't handle it. It doesn't scale well. Okay. So here's a few terms these are our official terms that we use. Typically, we more informally just talk about bugs and defects, and that's all we refer to in software. But more specifically, an error is the actual mistake, or we talk about it as a bug, so the actual mistake in the software. Now, have you guys heard the story? Why do we call them bugs? Anybody know where that comes from?
Wasn't a moth?
Yep.
That got into a computer system and into the hardware and was creating like a short or something?
Yeah, exactly. So there's this famous, way back when computers they had some physical circuits in them that could open and close. And so back in the early days, and there was some program they were running and it wasn't working correctly. They checked the code, and they couldn't figure out what was wrong with it. And they said, well, let's go look at the actual computer, the physical hardware. And sure enough, one of the circuits was not closing completely because there was a moth caught inside there. Okay, and so they pulled it out, stuck it in the notebook. Who is that? I believe that was Grace Hopper, the famous Admiral Grace Hopper. That was the person who was working on that, and she taped it down in her engineering notebook and said the first computer bug. And I think that her notebook is I don't know if it's in the Smithsonian or some museum right now. So that's where the word bug comes from. Okay? Some mistake in our software, even though it was a physical or hardware thing. Okay? But the error is the thing that's wrong in the first place, the problem in the code itself. A fault is the result of this error, and so that's what we would call a defect. Okay, so there's a problem in the code. Then what's the result of that problem? Maybe it returns a wrong answer. It doesn't do what it's supposed to. The result of that error. The failure is when you actually run the code and that fault executes. An incident is a symptom associated with that failure. And so these are the technical, terms officially that we're supposed to use. In reality, we call them defects or bugs, and we just keep track of them that way. We'll have test cases. What is a test case? It's a set of inputs and expected outputs. And the test case can pass because the output matched the expected output, or it can fail. Let me just show a quick example of a test report. So this is something that, so this is from Jira, and this is just an issue in Jira, and I have on this project, when you create that issue, you can specify, what kind of an issue is this? And you can call it a bug, a task, a story, or an epic. The issues can be like a user story. This is new functionality you want to create, but that's not the case here. Here it's a bug. We're saying, hey, there's something wrong. And we'll put a priority level on it. We have these different levels. The highest level is blocker. Blocker generally means that you cannot move forward until this, nobody can do work until this thing gets fixed. And so that's a very, very serious defect. Critical usually means something like it's crashing the application. Major means you have a major loss of functionality, a minor loss of functionality. Trivial, it's just like some little inconvenience. Maybe it doesn't look correct on the screen, but it still functionally is working. And so when you create a defect, you mark it as a bug, and you have to give it some priority. And this is from the user's perspective. It's not how hard is it to fix, but how big is the impact on the user. And then the key thing that I wanted to show here is this is a test case, and this is the result of executing that test case. This is kind of crowded here, but I require on projects that we create this table here. And so you have a list of actions and the expected behavior and the actual behavior and whether that passed in this test case. And the key thing here is that you give enough information to be able to reproduce this defect, okay, or this fault when it actually occurs, okay? And so if there's not enough detail here, the person who receives this struggles to reproduce it, and so this is an example of a fairly good one. Here, they gave the detail in terms of use this particular file as the test that you're putting in the run folder. Well, it'd be nice to know what are the data values, and did you give it a number of 1,000 and that's when it failed, or what? But at least they've given us a file name that you can look for that has the details in it. And these are the steps of what should happen, and this is where it didn't do what was expected, and so it failed. That's a sample of a bug report, a defect report. Do you guys have to fill these out, or do you receive these at all?
Every day.
Every day. That's your job. I was guessing there'd be some people that's what you guys do.
Yeah.
Every day. Any comments? Any best practices you have with reporting defects and or being the recipient of defects reports?
I say the environment. I don't know if that's on here, but environment is always really critical. Mm-hmm. Like, for instance, it's a really random thing, but that table doing the pass-fail and having it cut off, that's a Chrome thing. If you open it in Firefox, it renders properly.
Okay.
That's a bug in Jira itself.
Yeah.
Or it might be the bug in the Chrome browser and the way they're using WebKit or something. I don't know.
Yeah.
Environment as far as is really helpful. I like how you force them to do the actual behavior. Mm-hmm. So a big thing that's often missing in a bug is it's kind of like, all these steps and then this happens. And the developer's natural next question is, well, what were you expecting to happen? And it's not always self-evident, right? It's like, oh, look, it gave me 10. Yeah, that's kind of what I thought it was supposed to give. What is it supposed to give? And then, so like kind of you're not telling the developer like what they need to do to fix it, like go to this class and change it. You're saying, I expected the software to give me 12 and it gave me 10 because blah, blah, blah. And then it's like, oh, okay. And then you can actually have a conversation about it and figure out, if it's really as designed or if it is a bug and needs to be fixed. So the actual behavior is really important. And most people, because they're reporting it, it's self-evident to them. They're like, look at this thing that happened. And it's important to list the actual. We don't, at least at where I'm at, the test case is a separate issue type that we link the bug to. So we say, like, we were running this test case and it failed at, verification point blah, and then give the details on the bug and the bug report itself and reference the other issue type. Mm-hmm. But yeah, that's really good practice to have that there.
Yeah.
The environment, though, is what trips up a lot of people initially.
Yeah, that's great. That's great. So environment, here we're, I guess this one is not running on a mobile device, but like if we're running on a mobile device, which device were you running? Oh, I was running on a Galaxy S6. Which version of Android did you have? Oh, it was Android, Marshmallow. And so those things are really important because maybe it's fine on a different device, on the device that they originally tested on, it worked fine, but on yours it was different. And so those are really important. Capturing enough details to be able to reproduce it. Really important. Yeah, and it's interesting you mentioned the expected and actual behavior. I think that's super important. If the expected behavior, if there's disagreement on the expected behavior, that's not a defect issue. That's a requirements issue. What should it do? That's more a design and requirements issue. And that's where we get into battles of misunderstanding what it's supposed to do. And that's something, the earlier we can determine and agree to what it should do, the better. And then what it actually does, we're just testing. Yeah. Remove some of the emotion out of it and the finger pointing out of it. Okay, great. So let's walk through, I'll just mention as well the last two things, clean test, dirty test. Sometimes we know something works, but we write up a test just to prove that it works, just to show here, we've got documentation that works. A dirty test, we'll create a test just to show we know something doesn't work, and so we'll write a test that demonstrates that it doesn't. We have a record that it doesn't, and now we can justify working on it. And whether that means writing it as a automated test, like I'll show you in a minute, or putting it in Jira or project management software, something like that. Concept of clean and dirty tests. Okay, so let's look at just a couple of these somewhat formal ideas. The problem with software testing is it's impossible to test everything. It's just, we do not have time. If you have any software that is, anything more than just tiny and trivial, it's impossible to test all possible input values and all possible output values. So we have to figure out how do we narrow the space down to what we can test that is representative of the possible inputs and expected outputs so that we have confidence in the software. Okay? So if we think of the program as a function, like a mathematical function where we give it some inputs and it gives us some output. Okay? And most all programs are that way. Maybe the output is actually displaying something on a screen, but still it's giving us an output. We give it some parameters, some values, like our car rental agency. We give it some inputs like, here's a date range. I want to be able to check out a car or rent a car on this day and return it on this day, and I want this kind of a vehicle, and it should return to me a list of vehicles that are available and prices for them, for instance. Okay, so that's a function. I give it some inputs and it gives me back some outputs. What are those things? So if we think of it in that way, one of the ways of testing is boundary value analysis. The idea is that bugs tend to lurk around the edges, around the boundaries. And this is a common sense kind of a thing that we would typically do. And so if our parameters are in some range of legitimate values, then we can look at what are the legitimate values, what are the illegitimate values. So like, for instance, in setting the pickup date for a car rental agency, we might say legitimate values are any day of the year, okay? So a illegitimate value would be something like March 33rd, okay? That should not be a value. That would be outside of the range of valid values, right? There is no March 33. And so what we might do is we might test along that boundary. Let's test March 31, and let's test March 32 and make sure it rejects it. It shouldn't accept March 32, okay? And chances are good that March 31, if there's a bug, it might lurk around March 31. So how do we choose these test cases? Again, even if we were just to say, I could test every single day of the year, and okay, that's not too bad. But of every possible year, that's 365 test cases. If you're having to do that manually, what a pain. Who wants to go and enter January 1, January 2, and test it each time? Hopefully you can automate it at least. But even better, can we choose some representative values that are reasonable? And so that's what boundary value analysis tries to help us do. The first thing is single fault assumption. We're assuming that defects tend to only deal with one of the input values and not a combination of the input values. So here, we're going to try the minimum, the min plus 1, some nominal value, the max minus 1, and the max for each of the variables. So this is for variable x1, for variable x2. So this might be for the pickup date and for the drop-off date, for instance. So we would try those. So we're not going to worry about all of these other values out here, but this is representative enough. And so we can calculate, okay, so that's going to produce 4 times n, if they're n variables. Here there's 2 variables. So 4 times 2 plus 1. So that's going to produce a total of 9 different test cases we need to create. And so we can predict how many test cases there will be. It's all mathematical. It's fairly formal and logical. Okay. So that's with the single fault assumption. Oh, whoops, I didn't show all the others. We can reject that single fault assumption and say, well, sometimes we think the error is when there's a combination of X1 and X2 of each of them. And so then we can look at also on the corners here, in each of the corners. And so then we're going to have, 6 times n plus 1, or 6 times n, I don't remember, something like that. It's actually to the power of n, number of different test cases, so it's going to increase it significantly. And we might also say we want to go one past the boundary value. So let's give it illegitimate values as well. So that's just, again, just a formal way of trying to decide what things should we test. Okay, so that's boundary value analysis. Another one, just as a sample, is this concept of equivalence class testing. So here we're going to partition our input range into mutually disjoint sets. Okay, and so we'll start with like this bottom one, months for the number of days calculation. So we want to just deal with months that have 30 days, months that have 31 days, and then February, which is its own beast. It's, just kind of weird and funky, right? So all of our months of the year can fall into one of these 3 disjoint sets. No month fits into 2 of these sets. And so the idea is, now that we have these equivalence classes, we can just pick one element out of each class, and that can represent the entire class. So we'll pick February and June and January, for instance. And that's enough. We don't have to test all 12 months. We'll just test 3 months. And so we're narrowing the space of our inputs and claiming that that's representative. That's the concept of equivalence class testing. Right? And again, that's probably pretty straightforward, makes sense. Yeah, common sense, could have thought of it, but we have official names for them. Any questions or comments on either of those two? So we have boundary value analysis and equivalence class testing.
I guess I would say the order that you run them in. So usually, like with our automated tests and things, if you go back to the previous one, I'm trying to remember the word you used for it, the nominal one. We give it the softball test first, and we run that one first before we go the others. And then typically, especially when it's automated, we do the just outside the boundary as well to make sure. It's just a common error, starting to count at 0 instead of starting to count at 1. Somebody just really quickly, when you're supposed to have a limit on a different number.
Yep. So. Good. And what would you say these two testing techniques, are these black box or white box testing?
They're definitely black box. I mean, you can automate the black box testing and do that with certain tools, but it's black box in the sense of like you're seeing an input field and giving it that. I mean, I guess you could apply it to unit tests too, but
yeah, we definitely do this at a unit test, but you don't have to know what's inside the code.
Yeah.
You just have to know what's the method call. And so it's a black box in terms of the method call. Yeah. Now there's other kinds of white box testing methods, things like path testing. And let me see. So path testing might be if I've got that's a white box test, and so I'm looking at the code and I see, oh, there's a series of steps, and maybe there's an if then else in there. And so because I see there's an if then else, I'm going to make sure I give it a test case that makes that if be true, and a second test case that makes sure that that if evaluates to false, so that I take both possible paths through there. Okay. If this was a black box test, I wouldn't know if there's an if then else in there. I don't see it. Okay. And so I don't know to make sure that I take both paths. But because it's white box, I can see the algorithm, I can see the code, and I want to make sure it takes every possible path through there. And we can actually calculate things. So we have software metrics, and this is a great place where that comes up. One of the metrics we have is something called cyclomatic complexity. So you can look at a method and you can calculate how many possible paths there are through there, and that gives you a number, which is the cyclomatic complexity. And so if you get a number of like 7, that means there's 7 possible paths. So there's several if-then-else statements in there. And if you have a nested if-then-else inside of another if-then-else, it increases that cyclomatic complexity. And we can run those metrics on our code and get some warning signs. If we see a method that has a cyclomatic complexity of 37, oh, that's a warning sign. That's a really complex method. That's going to be hard to test. I've got to come up with 37 tests for that one method just to make sure I get all of the possible paths through there. And logically, it's going to be hard to understand that method. If there's any way I can break that method down into smaller methods so that the cyclomatic complexity is smaller, is lower, it's going to be more maintainable, more testable. And so those metrics are useful for us to figure out what do I need to work on. Yeah. And how do you do that? So, if I've got a method that's got all these, nested if-then-elses, maybe I can take the innermost set of if-then-elses and pull them out into their own method and replace it with a method call. So now I can test that innermost portion by itself and not connected to all the other complexity of the method. Okay, so those are some of the techniques that we can do, is we can pull those things out. Okay, so those are just some samples of some of the kinds of testing that we'll do. What I want to end our time together with is this concept of test-driven development, because I'm a big fan of it, and it's really caught on in a lot of organizations. A lot of companies are doing it. It came out, it was originally used way back in the 1950s on Project Mercury. So a NASA group down at the JPL that kind of started using this idea, but they didn't advertise it. It didn't really become popular until with Agile, it fit in perfectly. And in the late 1990s, 99, around 2000, with extreme programming, test-first design, or what became called test-driven development, was proposed for the first time. And since then, it's taken off. Okay, so the idea is that it's primarily a design approach, but it involves testing, and but really it comes down to designing your software. Okay, what you'll do is normally the normal approach is you would write some code, and then you would write a unit test to check to see if that code is correct. But TDD flips that in the other direction. It says before you write any code, write a unit test. So like what we saw before with the step and the expected behavior and the actual behavior, you would define for this little bit of code, like this one little function, how am I going to call that function? And if I give it this value, what should it return? So if I give it a 7, should it give me back the character W? And so you create a test before you write the code. The advantage of that is that it causes you to think about, first of all, what should the code do, and how am I going to call it? Okay, and then go and implement the code. Normally, we assume that you know what it's supposed to do and how you're going to call it, but we don't check that. And so you just go ahead and start writing the code. This forces you to check that. It verifies that you know what it should do and how you're going to call it. So we'll see an example here in a second. So we're going to write a unit test, then write the code to make that test pass, and then we're going to do this thing called refactoring, which means basically we're going to clean up the code in the test. And so I'll walk through that here in a second. These unit tests that we're going to write are automated. So we can just click a button and we can run 1,000 of them in a few seconds. Okay, they're not manual tests. They're things that are in software themselves. And again, that's what forces the programmer to consider the use of the method before we actually implement the method. Okay, so this is the context. This first row here is kind of the traditional way that we have developed software. I was talking about that earlier. We would create a high-level design and architecture, and then we would go and we'd create a detailed design. Usually this would be very detailed UML diagrams. Okay? And then we would write the code to implement those UML diagrams, and we would write the unit tests to check that our code was correct, and we would iterate. And then we would do larger scale testing, system testing, functional testing, acceptance testing. With test-driven development now, instead, we're still going to do that high-level design and architecture, but instead of doing detailed design and going into filling in completely our UML diagrams, we're not going to put all the details in. We'll just have the high-level diagrams, and instead we'll use TDD in order to figure out what are the details. What are the class names for all the classes? What are the methods? What parameters should they be? We'll figure those out as we write a test. So write one test, write some code, refactor. And then that cycle will continue. And we'll still do the large-scale testing at the end, the functional testing, system testing, regression testing, things like that. So that's the big picture there. Okay. So let's do it. Just jump into an example. So let's say that this is what your task is. It's a fairly small task. Let's say you're supposed to write a function that ensures that passwords meet the following criteria. The passwords need to be between 6 and 10 characters long. They need to contain at least one digit and contain at least one uppercase letter. Okay? So every website, mobile application, whatever, that checks a login and a password will do something like this. You know, these are the rules for passwords. Okay? Everybody understand the requirements? Okay. So where do we start? With TDD, we start by writing a test. So this is my first test. So this is actually code that we've written, but the code is using a framework called JUnit, and it's code written to test other code. Okay? So the idea here is I've got a test called, this test method called testValidLength, and what it does is it creates an instance of a class called passwordValidator. This is all in Java, by the way. Okay? So passwordValidator must be some kind of a class. I'm creating an instance of it. And then here, PV, that's my instance of passwordValidator. I'm going to call the method isValid. So I'm going to give it a string, ABC123, and that I'm asserting that isValid, when I give it ABC123, it should return true. That should be a valid password according to my definition back here. It's between 6 and 10 characters long. It has at least one digit and one uppercase character. And so I'm claiming that that should be true. So there's a test. Before I write the code isValid or create the class passwordValidator, I've written a test that says what it should do in the end. Now, I've actually, so some of this stuff in here is just stuff that's needed for JUnit, and so we can ignore that for now. But this line down here, assert equals, that's the teeth of the test, I would say. Okay? So that's where either the test is going to pass or it's going to fail when that line executes. Okay? And in here, I have made some decisions. Well, I'll get back to that. So here, I can't even run the test yet because I haven't even created the passwordValidator class. Okay? And so that needs to happen. But here's where I made some design decisions. I decided there's going to be a class called passwordValidator. It's going to have a method called isValid, and it's going to accept a string as a parameter, and it's going to return a Boolean. Those are all design decisions I made while I was writing the test. Okay, now, I could have made those decisions while I was creating my UML diagram. Or I could have made those decisions while I was writing the code. But instead, I made the decisions while I was writing the test. Okay? All right. So the next thing I might do then is go and write that code. So now this is my class passwordValidator. It has a method in it called isValid. It accepts one string and it returns a Boolean. And this is now the body of that function. It's going to check to see if that parameter's length, so if password's length is greater than or equal to 6 and less than or equal to 10. If it is, then it's going to return true. Otherwise, it's going to return false. So it's not doing everything that the code's supposed to do. It's only checking the length so far. Okay? It's also supposed to check for an uppercase character and for a digit in there, but it's not doing all of that yet. Okay? All right, now I don't expect you all to know Java, but I'm thinking you can look at this and you can kind of see what's going on. That, you know, there's an if, and it's returning something, and that's a Boolean value that it's returning. And here's our isValid method. Okay? So this will all compile, and I can run my tests. And so this is an example of what, you know, an IDE might look like. So here I've written my code, I've written my test, and over here I can just click on this little green button. It will run my one test, and if it passed, I'll get a green bar. If it failed, I'll get a red bar, and it'll tell me down here which line failed. You know, and it would probably come back here to this assert equals and point to that line and say, oh, that line failed. It returned false instead of true. Okay. But here, it passed. Everything worked great. Okay. Any questions so far?
So if you were trying to practice this, would you have written out the other tests that tried, you know, the boundaries and the different would you have done that before you wrote even the first line of code? Or do you do like what you did there where you had like the first test and then you covered the first part of it and then the next test and the next part? How would you typically do that?
Yeah, that's a great question. And I would say the answer is no. You don't want to write all your tests. You just want to write one test, and even the simplest test you can think of. And then write just enough code to make that one test pass. So like I did here, I didn't try and cover all of the possible cases. I wrote just enough code to make that test pass. In fact, I could have even just written here, return true, and that test would have passed, okay? But I didn't want to do a little bit more, you know? And I might keep down, you know, just have a little notepad on the side where I'm writing down, oh yeah, make sure I don't forget to write a test to do this and a test to do that and test to do this, because I know I'm going to get to those other tests eventually. But I just want to do it iteratively, a little bit at a time, because what happens is you learn something every time, and it changes the way you think about the code with every little thing you learn, okay? And if you go and write all of your tests, then you might be reluctant, you might not have that advantage of learning in this iterative style. So we'll come back to that here in just a second. Maybe you'll see it as we walk through that. Okay. So the next step here, just to finish this out, so there's 3 steps in the test-driven development process. The first one is you write a test, which we did here, and then you write the code just enough to make the test pass. And then the third thing is you refactor both the test and the code. And so what is refactoring? Let's see, do I have that here? Yeah. Refactoring is this great word. It means that you're going to change the structure of the code without changing its behavior. You don't want it to do things differently, but you want it to be organized as cleanly as possible. Okay? So some examples of a refactoring might be you just want to change the name. You decided, oh, I chose a really poor name. That is valid, maybe wasn't a good name for that method. Let's change it to a better name. Or you want to extract a method out. Maybe your method is too long, and so you're going to break it up into 2 methods. Okay? Or you want to take something that's a method call and instead just do it in line, the opposite of extracting the method. Or you want to pull something up to a parent class or push it down to a child class. And some of these IDEs have automated tools for helping you do these refactoring. But the main point is here that when you do a refactoring, it should not change the behavior, meaning what it returns. Okay? So I'm going to back up here, and so I finished, I ran the test. I don't want to change its behavior, but I just want to look at this and say, did I write this in the best way possible? So as a programmer, I would look at this and say, well, is there a cleaner way? And I don't know. I don't expect you guys to know. What can be done that's cleaner here? Yeah. So as a programmer, I would say, well, okay, I created this thing that's an instance of this class. Did I really need to instantiate the class? Because I'm not storing any data in any fields or variables in the class. So we haven't talked about this. I don't expect you to know about the difference between static methods and instance methods. But I could change this to instead not create an instance, but just call the isValid directly on the class, which is what's called a static method. And so it cleans up my test. My test is now just 1 line instead of 2 lines. Rather than these 2 lines, it's a cleaner test. It's shorter. And so in order to make that test pass now, I just have to make a little change. I just add this one little word static in front of the isValid method, and that's all that had to happen there. Okay? And my test should now pass. Okay, so I just made a small little change to the structure of the code, but the behavior stayed the same. And I have this, JUnit test to be able to check to see that it stayed the same. Does it still pass? Okay, so then I'll look for this. Can I simplify this in any possible way? Well, this is a common simplification that we have in programming. Anytime you have something, if something is true, then return true, otherwise return false. Well, if this is true, return true. If this is false, then return false. Well, I don't even need the if and then return true. I can just return whatever this condition is. Because if this thing is true, then that's what I'm returning, true. If this conditional here is false, then I'll return false. So I can simplify it to just say this, return the result of that conditional. Okay. And again, I wouldn't expect you, without having written programs yourself, to know that. But as a programmer, anybody who's taken programming 101, 102 would see that and say, oh yeah, that, of course, I know how to do that, and that's just a common thing that we would do. So there I've refactored. I haven't changed the behavior of it. I just changed the structure. It's now simpler, it's cleaner code. All right, so I made those 2 refactorings. I can run my test right away, and I do this with TDD. I run my tests over and over and over again really rapidly and check to see, okay, made a little change, did I break anything? Made a little change, did I break anything? And if you did, you know what you did. You just made the change 2 seconds ago, and so you know what you did to cause the problem, so you can go back and fix it. It's not like it's 6 weeks later. You have to try and remember, what was I doing that day? You get immediate feedback. Okay. Another thing here that we might do to make this better, these things we call magic numbers scattered throughout our code, those can be a pain. What if, it's usually a business decision to decide, okay, passwords need to be between 6 and 10. Maybe in 3 months from now, they're going to change their mind and say, oh, passwords need to be longer. They're not secure enough. They need to be between 8 and 15. So I'd like to maybe make those things constants that are in a place where it's easy to change. So maybe I'll put them up here at the top of my class as constants, and I'll just refer to those constants instead now, okay, rather than having the numbers down buried in my code. Okay, so that's again a refactoring. I can run my test, make sure that didn't break anything. Okay, make sure I didn't make any little mistakes. Okay, so I'm done refactoring. So the next thing I'm going to do is write that second test. Finally, I got one test and the code done. So let's write another test. So now I'm going to give it a different test where this one should fail. The password is too short. It should fail. So I run that test, and it just passed already. So I didn't need to make any code changes. I'd already written enough code to make that test pass. Okay, great. So now let's go to the third test that I can think of. Well, let's do one where there's no digits in it. It's 6 characters, but there's no digits. And it fails. So I get a red bar. It tells me which one fails. My first 2 pass, but this third one is failing. And so I know that I need to modify my code and add to it to not just check the length of the string, but also whether it contains a digit. So here, this is this ugly stuff using regular expressions, but it uses this pattern matcher to say, oh, there better be a digit inside that password. Okay, so the password is between 6 and 10 characters, and it contains a digit. Well, that's kind of complicated, and I want to make sure I got it right, whatever. And so I can at least run the test and see, yeah, that works for that example at least. And I might write a couple more tests like that to make sure that it didn't just happen to work for that one example, but for others that also don't contain digits. Okay, and again, I look at it and I refactor. Can I make this more readable? Can I make it more cleaner? And I say, oh yeah, I'm doing kind of 2 different things here. So let's make those method calls. So that's what I did here. Here I'm changing isValid is calling isValidLength, which is a new method up here, which checked just the length of the password. And it calls contains_digit, which checked that pattern. So I made my code a little bigger, but it's hopefully more readable now. Rather than just, the previous one was this, having all of this stuff together down here in this complicated return statement. Now it's it actually has method calls that describe what it's trying to do. Here we're checking the length. Here we're checking to make sure it contains a digit. Okay. And then I can run the tests. Oops. And I can run the tests and hopefully see that it passes with a green bar as well. Okay. So that, in my 20-minute explanation, is test-driven development. That's kind of the concept. It's kind of a radical thing in some ways. It's just a small change, but it can make a big difference on how software developers do their work. Now, what I did in some of my PhD research is I did a lot of empirical research on this. So I took hundreds of developers, some of them many of them students, some of them in companies, and I had them do essentially the same projects using traditional test-last programming, and then having others do them using test-first programming, or TDD. And I compared the results. Did one of them produce code that had fewer defects in it, or was simpler, or had, for instance, a lower cyclomatic complexity, was easier to maintain? And I did studies on all of that and reported that so that the rest of the software engineering world would know, oh, is TDD better or worse? In what ways is it better or worse? So that's the area of empirical software engineering, where we do all these controlled experiments and sometimes case studies to try and figure out what are the best practices, what should they use. And I'll just mention, one of the things that I created in my research here a while back was a simple database called evidence. Let's see if we can get it up. Evidence-based SE. And it turns out that a lot of people are actually referencing this. There it is. And so there's a variety of areas here. And so, like, for instance, TDD is an area, and you can see there are currently a total of 35 different studies that have been done on test-driven development, and these are just kind of like cliff notes of those studies. And you can go in and you can see a little bit about them. Okay, so in this particular study, how long did it go? Where was it done? How many developers were there? And essentially, what did they find? And then here's a summary of what did they learn about TDD in that study. And so that's just in the area of software engineering evidence, or empirical-based software engineering, where we try and actually, as a science, study what we do in software. All right, guys, so we've got 7 minutes left, according to my watch. That is what I had on software engineering. What do you want to talk about? Any questions? Any terms you've heard, you wonder about? Anything you want to discuss yet?
Just thinking about if you go back to the V model that you had that talked about the verification and validation.
Uh-huh.
So in my mind, it feels like with this, what you're doing is you're essentially flipping code and unit testing and then putting like a little recycle loop on it.
Yep. You're exactly right. Flipping.
And that's kind of how I imagine it as far as when it goes through.
Yep.
I know, I think it's very true that if you put unit testing later, it gets abandoned later on in the project almost inevitably.
Yeah, it's exactly what my research and other people's research has done. One of the biggest advantages of unit testing in using a test-first approach is that it makes you do it, and you can't, cut it at the end because you ran out of time, which is what happens so often. Is you write code. A lot of times people will write some code, and they're supposed to write unit tests right away after they write that code. But, they're busy, they need to get on to something else, so they don't write it. And so they put it off, and maybe they even have somebody else write the unit test. And so the longer you have a separation between the unit testing and the writing of the code, the less likely it is to happen, and the more likely there's some misunderstanding there. It's interesting that the unit testing is usually written by the same developer that writes the code. And you could argue, well, that's bad because that developer has bias. They're not going to test their code in hard ways. They're going to make assumptions about the code and not test the boundaries, really well. And that can happen, but that always gets fleshed out at higher levels. And I think most software developers are, they have integrity, and they're not going to artificially try and be soft with their code in hopes that nobody will find out that it's not quite right, or so they don't have to work too hard. I think most of them really want their code to work right, and they're willing to test it fairly hard at a unit level.
Yeah, and also the other thing is I've seen projects that start off really well, and then in future iterations when stuff starts changing and the budget's a lot smaller for those modifications and things as opposed to a brand new project, is like maintaining them and updating them, and that becomes a really difficult part of it, and it gets lost. But when you force it to happen beforehand, the maintenance is built in with it, so
right.
You have the potential to lose a lot of that. That's probably the most frustrating for me, is when I've seen when a project had a lot of really good unit tests and then we get a modification on it and things change, and those are not maintained because they say like, well, we've only got $20K to add this thing. We're not going to go back and change all these things that we've now broken by making these changes, and then future releases suffer for that when it goes through. So it definitely is a good practice. It's just really hard to convince as far as on certain projects and things.
Yeah, I understand. One reference that I might have in those situations, there's a book that I've been going through with my students, Working Effectively with Legacy Code. Okay, and this guy, Michael Feathers, his definition of legacy code is any code that doesn't have unit tests around it. Okay, so that could be code that you wrote this morning, but if it's doesn't have an automated test on it, then it's legacy code. And so he gives a bunch of techniques for how to get code that doesn't have tests under test, how to make it testable. Getting to what you're talking about, one of the problems that I've seen what you're talking about happen many times. And so even if you have unit tests, people will sometimes, they'll go and they'll start making a bunch of changes and then not bother updating their unit tests. Okay. Often I feel like it's just a lack of discipline. You can do all of those making a changes in really tiny steps. Make a small change, modify the unit test if you have to, in order to reflect your small change because functionality is changing. Okay, and it gives you feedback right away. If you just have the discipline to do all of those changes in really tiny steps, then you can keep the unit tests maintained. The problem is when you just say, oh, we don't have time for unit tests at all, so we're just going to not deal with them for a week. Well, that's when you get in trouble. If you take the time, it's kind of that quality is free if you are willing to invest in it. If you're willing to take the time to maintain this little unit test right here when I'm making this little change, it's going to pay for itself in the end is typically the case. But convincing people of that can be hard. Yeah. Good examples, good anecdote. Yeah. Okay, we're at 5:59, so we're pretty much done. I guess let me end with two things. One is I put another quiz out there. I don't think it's probably going to affect your grade at all, but I encourage you to take it and just see, did you catch what I think you should have caught? And it's just some terminology and stuff. And so it's open. I think I left it open until Monday at 3 p.m., something like that. So I encourage you to take the quiz. If you've got questions that come up, feel free to post them in the forum, and I'll be happy to answer questions on software. I believe Kurt's going to be back on Monday, and we'll pick up on the last couple of weeks of the class and of the whole series of classes. And so I don't think I'll be there on Monday, but if you have anything that comes up, feel free to post it. I'm on the PolyLearn course, and so I'll see those questions and I'm happy to answer them. And so then the last thing is just a thank you. Thanks for accepting me, letting me come in and share with you some stuff on software engineering, and I wish you guys all the best. And I know you're in many different areas and domains, and some of you, this stuff was just what you needed. Some of you, it's like, I don't really interface with software people, but I hope you got something useful out of what we talked about. So thanks for your time.
Thank you very much as well.
Yeah. Yep. All right. I will see you whenever. Best of luck.
See you later.
Thank you.
Bye.